Okay, so thank you, Felix, Matthias, Stefan, for having me here, for the invitation to be here. It's quite a pleasure to be back to Mainz again. I've seen it last time 10 years ago, and it looked totally different. So, wow, great job. Okay, so I hope you enjoyed your tour this morning. I hope you learned something from it. My lectures, as was just announced, will be on precision QCD. And I would like to start by answering the question, why do we care about QCD? Why is QCD important? Why do we talk about it all the time? And I will start with this plot, which I am pretty sure that you've seen it in the past multiple times. It shows you a comparison of data with theory predictions coming from multiple processes that involve gauge bosons, tops, Higgs, jets in the final state. A comparison that includes data from 7, 8, and 13 TeV collisions at the LHC. And what you can see is that there is a great agreement between our predictions and data over many orders of magnitude for the cross-section. The thing that I would really like to emphasize here, and I would like you to keep this in mind, is 10 years ago, we were nowhere near where we are right now. 10 years ago, we haven't yet observed the Higgs. We haven't seen yet TT bar W or TT bar Z. Even TT bar Higgs was actually only observed within the last year. So we've made giant steps experimentally forward, and that's really a great progress. Accompanying that progress is our theory predictions, the progress for the theory predictions. We wouldn't have had this great agreement if our theory predictions were not at the same level of precision of our experimental data. And QCD affects the predictions of all these processes. Corrections from QCD can be larger for some processes than others, but it's everywhere there, and you need to understand it to be able to get such a picture. So this plot actually has confirmed that the standard model so far is a good theory. It's able to describe our data. The theoretical framework we are using to calculate these predictions seems to be okay also, because we are able to get this agreement. So it's a pretty important plot. Okay, so QCD is actually used at the LHC to enable discovery. And one of the important examples is Higgs production. So Higgs, as you know, can be produced in multiple ways. The dominant production mode is gluon fusion. And then it decays also in multiple ways. So this is, for example, an example from Atlas, where the Higgs decays into a WW star, and then it decays leptonically after that. So you have missing energy in the final state. And we are looking at the zero jet bin here. So this is potentially a difficult search. Why is that? For the W case, since you have neutrinos in the final state, there is a missing energy. So when you reconstruct the transverse mass, which I don't think you see, I don't see it, so probably you see it. So this is a plot for the transverse mass. Okay, I cannot bring this one down. Okay, so it's potentially a difficult search because you have missing energy in the final state. So the signal does not, or the final state, the reconstructed mass, the transverse mass, does not look like a bright Wigner peak. Instead, it just looks like smooth axis over the background. And when you have overwhelmingly large background, this can be difficult to see. So you absolutely need to understand your signal very well. You need to understand your background very well. In this case, the irreducible background is coming from WW, which has the same final state as our signal. There are other backgrounds. Some of them are reducible. The reason we are confining ourselves to the zero jet bin is that experimentally, a jet width was imposed to split our cross-section into 0, 1, and greater than or equal to 2 jet pins. The reason for that is that it gives you the chance to enhance, to design cats that enhance the signal over the background. That's what was done here. For example, the TT bar background, which appears here as negligible, this is the one in yellow here, originally is not negligible. It's large. But when you impose the jet V2, TT bar decays into 2 Ws and 2 jets, you remove to a large extent this background, which is why it appears small in this case. So clearly, a lot of efforts went into understanding the signal and the background here, but there are other theoretical issues associated, for example, with the jet V2 that is applied experimentally to enhance the signal. This jet V2 can introduce some theoretical uncertainties. They come under the name logarithms of the jet V2, which can be large. So you need to understand them. You need to understand how to deal with them theoretically. For example, should you resum them or not, and so on. So this particular analysis, it received a lot of theoretical work to bring it to the level where we are right now. And this is just one example where QCD was important to have a discovery, to make a discovery in the first place. Okay, when you discover new particles, you need to understand their properties. For example, we want to understand the Higgs coupling to other particles. So this plot here, what it shows you is the signal strength, is the ratio of what we measure divided by the theory prediction. So our uncertainties on the theory prediction enter in the denominator. And various decay modes of the Higgs here are shown. I will focus on the first three ones. Those are the so-called discovery channels. And there are three types of uncertainties that are listed in here. In black is the statistical error. In blue is the total systematic error, including theory. And then just to see how much of it comes from theory, they show the theory uncertainty in red. And if you look at this, at Higgs to gamma gamma, ZZ star, and WW star, I don't know if you can see the numbers very well, you will notice that the largest error here is the statistical one. However, this is a plot from LHC run 1. I haven't seen yet a plot for including LHC run 2. So this statistical uncertainty is being worked on right now as we speak by LHC run 2, and it will be brought down significantly. It won't be any more the dominant uncertainty. So it's followed then by the systematic error, which in the three cases, as you can see, is the second largest one. And then if you compare the blue and the red numbers, you will see that a large fraction of the systematic error comes actually from theory. So clearly, understanding the Higgs properties very well will require us to understand theory and improve our uncertainties on the theory side. Theory uncertainties come from various sources. They come from the renormalization and factorization scales, which are in physical, as we know. They come from PDF uncertainties. They come from parametric uncertainties, such as errors on alpha S and the quark masses, in particular the B mass. All of these need to be worked on and brought down to a level that allows us to make meaningful studies and compare our theory data and learn something from it. So we needed QCD to make a discovery. We needed it to understand the properties of what we had discovered. It's also important to understand QCD when you are looking for new physics. So what you do is you try to calculate the backgrounds very well, especially in the cases when they are overwhelming for the signal. You needed to understand your backgrounds. So one thing that the standard model cannot tell us anything about is the dark matter. The standard model can only describe 5% of the visible mass. 95% is dark matter and dark energy. And the standard model cannot say anything about it. So dark matter, there are multiple ways of searching for it. One of them is searching for it at colliders. It does not decay in our detectors, so it appears as missing energy. And one of the most model-independent searches is actually to look for missing energy in the final state. So if the dark matter is produced with other standard model particles, for example jets, you can use those jets to trigger on the missing energy. And this is here an example of a search for jets plus missing energy. Here we are looking at invisible Higgs search, a Higgs that decays into something that we cannot see, like dark matter. And you can see that there are lots of backgrounds for this particular signal. They are all listed in here. The dominant one is actually this light blue one, which is coming from Z plus jets, where Z decays into neutrinos. So you have a missing energy in the final state plus jets. There are multiple ways you can predict the background. You go and get it directly from theory, or if you want to minimize the impact of theory uncertainties, you use the so-called data-driven methods. So you use your experimental measurements as much as you can, and you use the theory input as little as you can to not be biased by the theory uncertainty. So in this case, for example, the prediction for Z plus jet, the way it was obtained, was to take the ratio of the Z plus jet calculated from theory to W plus jet calculated from theory, multiplied by the measured W plus jet rate. And the reason it's done like this is that W plus jet has higher statistics than Z plus jet, for example. So you're taking the ratio of these predictions. The idea is to try to cancel as much as possible uncertainties coming from PDFs, scale, and so on. And the good thing about W plus jet, or you can use also gamma plus jet. The good thing about this is that they have similar QCD behavior. They behave in the same way under QCD. So when you take the ratio, there is a good chunk of cancellation of uncertainties, but it's not total cancellation. And in fact, when you look at the table on the right-hand side, this is exactly what you see. This is showing you several systematic uncertainties that affect this search. Some of them are experimental, but the dominant ones are coming from the ratios that I just talked about, W plus jet over Z plus jet, or the inverse of that, or you can use also Z plus jet over gamma plus jet. You can see that the uncertainties are the largest on these ratios compared to everything else we have. So again here, there is a room for improvement. So you can see that QCD is entering everywhere, and you need to understand it pretty well if you want to really discover, look for something new, understand the properties of what you have measured. You need it for everything. It drives the dynamics of physics at the LHC or at our Hadron Colliders. So the aim of my lectures is to give you some basic understanding of QCD, focusing on its perturbative aspects. I will try to demonstrate some concepts through calculations of key scattering processes, in particular the concept of infrared safety, and also the infrared singularities that plug our cross-sections when we try to calculate them. How do we treat that? And we will try to do that through some key processes, for example, E plus E minus 2 hadrons, or DIS, or Drillian. We will see all these examples of all these cases. We will discuss the physics implications of QCD on relevant LHC processes, demonstrating the importance of the interplay between theory and experiment. And this is going to be done in 4 lectures. Some of them are going to be on slides, some of them are going to be on the blackboard. Okay, so the first part of the lecture is going to be reviewing some basics of QCD that you know very well, but we need to go through them anyway. So let me just start. So what is QCD? QCD is the theory that describes strong interactions between quarks and gluons. It is a non-abelian gauge theory with the symmetry gauge group SU3. We have 3 basic ingredients for QCD: quarks, gluons, and the strong Kaplan constant, alpha S. Quarks by themselves, they come in 3 colors in addition to their electric charge, and the color makes them different from leptons in QED. And they have, of course, their anti-quark partners. Gluons are analogous to photons in QED, except that they have the color charge, and there are 8 of them. And like photons in QED, they interact with each other. And the fact that they interact with each other makes an impact, a very, very deep difference, as you will see later with respect to QED. The strong Kaplan constant is a running Kaplan constant, meaning it is small at high collider energies and large at small energies, and it's larger than a QED Kaplan constant. Okay, so this is our Lagrangian for QCD. It's our starting point for anything we do. It has 2 pieces. We have the F mu nu part, which has the kinetic term, or the kinetic terms for the gauge fields, as well as the gluon interacting terms. And we have also the fermionic part, which has the kinetic term for the fermions and the interaction term between fermions and quarks, for example. The capital D mu ij here is the covariant derivative, defined clearly here. And this is the field strength tensor, which has the terms, the gauge field terms that show the interaction of gluons with themselves. So the terms proportional to the strong Kaplan constants in the field strength are responsible for the gluon self-interaction, and this is what makes the difference with respect to QED. We have these TRJ matrices. These are color matrices, and they are the generators of SU3. And QCD interactions do not depend on quark flavor, meaning all the quarks interact with in the same way with gluons. The only interaction that makes differences between fermions is the electroweak interaction. So we will next split our Lagrangian into the quark and gluon parts, and we will look at them in detail. So quarks, as we have said earlier, they come in 3 colors. This is the part of the Lagrangian that describes them. So the fundamental representation of SU3 has 8 generators, and they correspond to 8 gluons. I and J refer to the color indices in the fundamental representation. And an explicit representation for these generators in terms of, can be written in terms of the Gell-Mann matrices, lambda A, where the relation between TA and lambda A is TA is half lambda A. And those are the generators shown explicitly here. the gluonic Lagrangian is also pretty simple. The field strength defined in the previous slides contains the SUT structure constants FABC, and they are antisymmetric, and they also satisfy this commutation relation between Ti and Tb, shown in here. And this is just a picture here of some of the identities that you can obtain just by working your Corel algebra. For example, you can immediately say that this diagram here is going to give you 0, just because when you work out the Corel algebra, you see that it's corresponding to a trace of Ta, which we know is 0. Our normalization in what will follow will be such that the trace of TATB is TR times delta AB, where TR is 1/2, just to be clear about the normalization. There are also useful relations that are typically used in our calculations. Yeah?
I have a quick question. I'm a little unfamiliar with this notation, the diagrammatic notation, because this is not a Feynman rule, correct? This is some matrix.
This is just to show you the Corel structure that you can work out by writing your Corel structure. You can get some relations. For example, as I said, you can immediately say that this is 0. This is just to tell you that based on the Corel structure of, if you write down the Corel structure of this, you get something that is proportional to TR times the propagator. It's just...
So these are like really Feynman diagrams, but you're just omitting something.
I'm just showing the Corel structure, what it gives you there, yeah. So, again, these are some useful relations. You can tell that you will have a CF in your result if you have a gluon emitted from a quark, and it comes from sums of this form here. Typically, we use this relation between CF and NC. You will see that I will use it in the future, so I'm just putting it here to define it. You know that if you emit the gluon off another gluon, you will have a CA in your result. And there is also the Fierce transformation, which is typically used to simplify the Corel algebra. For example, if you have 4 Ta matrices, you can reduce them down to 2 Ta matrices just by using this Fierce transformation.
This also depends on the scale, right? So you have to choose how many colors you have. Like if you have like smaller energies, you don't have as many colors. You understand what I mean?
No, I don't.
Yeah. No way. Yeah. This is with flavors. Yeah.
This is just the Corel algebra, nothing special. It's just the Corel algebra.
Thanks.
We're talking about this here, right? All right, so gauge invariance is a very important concept. It leads to the renormalizability of QCD. It defines the way QCD interactions are. So we always emphasize it here. So QCD Lagrange is invariant under local gauge transformations, and this means that redefining the quark and gluon fields at any point in space and time does not change the physical content of our theory. So this is important. So the quark and gluon fields, as well as their covariant derivative, have transformations under have these gauge transformations shown in here explicitly for the fermion, for the covariant derivative of the fermion, and for the gauge field. And of course, the anti-fermion also has similar gauge transformation as well as the field strength in such a way that when you put all these pieces together, you will explicitly show that 1/4 f mu nu times f mu nu is actually gauge invariant, and the same for the fermionic piece. The important thing to keep in mind here is that the field strength alone is not gauge invariant. It's only the product that's gauge invariant, unlike what we see in QED. And this is due to the self-interactions of the gluons, as I said earlier. A mass term of the gluons would violate gauge invariance and therefore is forbidden, unlike the quarks, which can have a gauge invariant piece. So this is all just concepts I'm reviewing here quickly because it is something you have seen, but we do have to start with it. Gauge fixing is also very important. So just like in QED, we can't invert the quadratic part of the gluon Lagrangian to obtain its propagator. So we need to add a gauge fixing term that depends on an arbitrary parameter xi. And in covariant gauges, this gauge fixing term would look like what I'm showing here. 1/xi times d mu a mu squared. Typically, we work in Feynman gauge, where xi is equal to 1. Landau gauge would correspond, for example, to xi equals 0. And so in that case, the gluon propagator, once you include the gauge fixing term, the gluon propagator becomes just what I'm showing here. So it's g mu nu minus 1 minus xi k mu k nu over k squared times the Corel factor. And you go ahead and you use it in your calculations. You can choose to work in Feynman gauge or in other gauges, but there are consequences for whatever choice you make. So the gauge fixing term breaks gauge invariance, and physical results should not depend on this parameter xc. And what looks like a problem, you can always use it as an advantage, because you know that physical results do not depend on xc. You can check at the end of the day whether your calculation is actually xc dependent or not. And when you are doing complicated calculations, this is actually a very interesting check to do. So your result at the end of the day should be free from xc. So the gauge fixing term breaks the gauge invariance. You have to recover it. So in covariant gauges specifically, the gauge fixing term must be supplemented with the ghost term. In physical gauges, you don't need this. For covariant gauges, you do need this. So this ghost term will remove the unphysical longitudinal degrees of freedom. And so this is the ghost Lagrangian that you have to introduce, where eta here is a complex scalar field. And the corresponding propagator for the ghost will be I over k squared times the color factor. So the gluons, when you work in physical gauges, have only 2 degrees of freedom. When you work in the m-physical gauges, they have 3 degrees of freedom. One of them is m-physical, so it has to be removed. And so we introduce the ghosts to remove the m-physical degrees of freedom. So at the end of the day, your gluons have 2 degrees of freedom only, if you are working in physical gauge. If you are using Feynman gauge, you will have to include your ghost terms. Axial gauges. You can choose an axial gauge by introducing an arbitrary direction n, and you can choose n for calculational convenience, so you can choose it to make your calculation simple. So in axial gauges, the term that you add is minus 1 over xc times nu times nua squared. And in this case, the gluon propagator becomes more complicated. It takes this form here, which is more lengthy than what we have seen before. But if you work, say, in the light cone gauge, n squared is equal to 0, xc is equal to 0. So this entire term here goes away, and you are left with this piece, the first 2 pieces. So you have only, as I said, only 2 degrees of freedom for the gluons propagating this gauge. Hence, we call it the physical gauge. And you can check that this is the case by using these 2 constraints. If you contract with the gluon momentum, you should find 0. And if you contract with this n mu that you have introduced early, you should see that you have 0. So this is for physical gauges. For n-physical gauges, you have only one of these constraints, namely d mu nu k nu equals 0. And here we're talking about on-shell gluon. Okay, so this is a list of Feynman rules. You can take them from any source. I took them from this book, QCD and Collider Physics by Alice Sturry and Weber. This is a very interesting reference. It has lots of, it describes lots of physics concepts that you can look at. So it's one of my favorite books, and you can use your favorite Feynman diagrams as long as you are consistent within your calculations. Everything is fine. Okay, the running coupling. All couplings, whether they are QED, QCD, or electroweak couplings, they all run. They are not constant. And what this means is that they depend on the momentum scale q squared of the studied process. And again, because the gluons interact with each other, these gluon self-couplings lead to a profound difference between QED and QCD running of the coupling. So let's start with the QED case. And let's look at the QED beta function and look at the evolution equation of alpha of q squared. And I'm going to look just at the contribution from the electrons in this case. So the evolution equation says is q squared d alpha over dq squared equals beta QED. And we're taking just the first term of the beta function. So you take this and you solve this evolution equation. And what you find is this result in here. Alpha of q squared equals alpha 0 divided by 1 minus alpha 0 over 3 pi log of q squared over e squared, the electron mass squared. The important thing to notice here is that we have a minus sign. Now, as your energy grows, as q squared grows, your log will grow, and the denominator becomes smaller because of this minus sign. And what this means is that our coupling constant will grow with energy. At some point, it will hit Landau pole when the denominator vanishes. And so we say QED is strongly coupled at high energies. So the coupling constant grows with the energy. This is something that is completely different in QCD. In QCD, when you consider the QCD beta function, the gluon self-couplings reverse the sign of that denominator that I showed you on the previous slide. So you will consider the contribution from quarks, gluons, and ghosts if you are working in a covariant gauge. And this is your evolution equation where beta, in this case, has an expansion in terms of, you can choose how far you want to expand it, but we will only take the first term in the expansion, this B0 times alpha S squared with a minus sign. So B0 is defined in here. B1 is shown also explicitly here. Now I'm taking just the first term and I'm solving the evolution equation, and this is what I get as a result. Alpha S of Q0 squared, the starting scale for the evolution, divided by 1 plus B0 alpha S of Q squared log Q squared over Q0 squared. So here we have a plus sign, and this is pretty important. What this means now is that as my energy grows, as Q squared grows, the log here grows, the denominator becomes 1 over this becomes smaller. So that means that the strong coupling constant when I go to high energies becomes smaller. And when I go to low energies, it becomes larger. This is the opposite behavior of the QED case. And that's very important for us. The fact that at high energies this strong coupling constant becomes small is what allows us to calculate our predictions as an perturbative expansion in alpha S. So alpha S becomes small at high energy, has high scales Q, the perturbative expansion improves, quarks and gluons are almost free, whereas when we go to low energies, the perturbative expansion fails, quarks and gluons interact strongly and confine into hadrons. And you can see here that I equated this equation here with this right-hand side to define my lambda QCD. This is a leading order definition. Lambda QCD is an important also parameter to keep in mind. It separates the region where we start to become sensitive to non-perturbative effects from the region where we can talk about perturbative effects. So this is a plot here that shows you the running of the strong coupling constant. The strong coupling constant by itself is not something that we can measure. We can measure observables that depend on alpha S. And then we take measurements, those measurements, in combination with theory predictions for those observables and extract alpha S from there. And that's what these data points that you see in here represent. And you can see they come from different data sets in here. Tau decays, DIS jets, heavy quarkonia, E plus E minus 2 jets, and event shapes, Z-pole fit, and so on, PP bar to jets. And they show you also the order of the prediction, the precision of the prediction that went into this fit. And what you can see clearly is the predicted running of alpha S using beta QCD agrees with these results in here. And you can see that this is happening over many orders of magnitude of the scale Q. So lambda that I have defined with this equation here is often called lambda QCD, and this is a fundamental scale of QCD at which the coupling blows up. And it's of the order of 0.2 GeV, or 200 MeV. And our perturbative expansions are valid only for scales that are much larger than lambda. Otherwise, you start to become sensitive to non-perturbative effects if you are close to it. Confinement in QCD. So QCD becomes strongly coupled at low energies, and we think that this leads to the experimentally observed behavior, observed confinement of quarks and gluons into hadrons. So we have no direct proof of confinement, but we've never seen free quarks or gluons in nature. So we think that they are confined inside hadrons. So it's assuming that confinement always holds, although we have no rigorous proof of that. This is something to keep in mind. And so this is a plot that shows you the potential energy for a system of a quark-anti-quark pair as a function of the distance between this quark, anti-quark. And what you can see in here is that this potential energy grows linearly with the distance r. And this is what we think is leading to the confinement. So what this means, if you take this pair of quark, anti-quark, and you try to separate them by increasing the distance, the potential energy will increase by itself. And at some point, a new pair of quark antiquarks gets created from the vacuum to screen the potential. This is contrary actually to what you see in electromagnetism, where this potential energy falls as 1 over R.
Sorry, one question.
Yeah.
Why do you have this different behavior for this different mesons? So for the lowest line you have something like 1 over R also as a potential. For the upper line,
I would say let's just focus on this line here. So to describe these other lines for you, I would have to go and dig out myself all the details. So I focus on this line because here it's totally obvious. The other ones I would have to go and check myself what they all mean. Yeah.
So how is this measured? Because you can't just pull the 2 quarks apart, right?
How are they measuring it? Frankly, I have no idea how they measure it. I don't know how they measure it in practice. As I said, you cannot measure it because you don't see the free quarks and gluons. So from here, you can deduce that if you really try to, because of the behavior observed, you try to pull them apart, it's not going to work because the potential energy is increasing. You can see that explicitly. Because of confinement, you will never take really a quark and anti-quark and really try to pull them. But I don't know, Matthias, can you measure it? If you were to measure it, how would you measure it?
This is lattice data.
Yeah, so.
This is the lattice calculation.
Right, so but if you can't really measure it, so. But his question, if you were to measure it, how would you measure it? Because you don't see free quarks and gluons, you cannot really. Simulation from lattice is all what we have. That's the only basically evidence that we have. Yeah.
So the lambda QCD, we start including more and more groups. Lambda QCD started to grow, right? And instead of being 0.2 GeVs, it becomes like 0.5 or point something, right?
Are you talking about the normal?
Why is that happening? Do you know?
As
You
you,
solve that equation but with more loops.
when you,
The one for getting lambda QCD, it's in the previous slide. The beta function, yeah. So if you solve the pole, if you solve that, including one loop, you get a lambda QCD that is larger. My question is, do you know why?
no, as you include more and more terms of beta function, you're going to be able to describe the running of alpha S better and better.
Yeah, you can get also the point where it's divergent, right?
As you move to lower energy, yeah. As you move to lower energy.
But lambda changed, right? When you put more loop, my question is, do you know why?
I don't think I understand the question, frankly.
The scale at which these non-perturbative effects become important is 200 MeV.
Right, yes. So if you go to lower.
It doesn't change, right?
Right, so as you go to low energy, you will be sensitive to these non-perturbative effects. But adding more terms to the beta function is going to improve your running description of alpha S.
I can ask you after the next.
Okay. More questions or? All right, so let's get to hadronic collisions. As you know very well, this is, well, I'm pretty sure you've seen this picture, so it's just theory, our theoretical view of what a hadronic event looks like when you collide two beams of, let's say, proton-proton. The hard scattering happens in the center. This is exactly where we produce our new particles, whether it's Higgs or SUSY particles, and so on. But along with, this is what's happening at high energy. This is what we can calculate perturbatively. But along with this hard scattering, we have also emission of radiation that becomes softer and softer as time goes. And then we become sensitive to non-perturbative effects. So hadronization happens at some point, and bond states get formed. This is exactly what we see in our collider. And you also have to understand your PDFs, taking your partons out of the proton, their distribution inside the proton, and so on. So there are many things happening here at different scales. And the reason we can actually predict something complicated like this with this simple formula is the concept of factorization, which separates, events happening, things happening at short distance from events happening at, or things happening at long distance from the interaction that we have just looked at on the previous slide. So what this Hadronic cross-section tells you is that you can convolute the PDFs, which are non-perturbative quantities. You can get them from a combination of data and theory predictions, and they are universal. And you have a Platonic cross-section, which is process-dependent, and this is exactly what we calculate perturbatively, given that we are at the point where the Hadronic interaction happens at high energies. There are, in principle, power corrections that are proportional to lambda QCD over Q. Q is the scale of your hard process. Powers of that. So this factorization formula was proven for some processes. We don't have a proof of it for everything else.
What are the axes? X1 and
These are Bjorken axes.
what?
Bjorken axes. We will see them again in some incoming examples. Mu f and mu r are these unphysical scales, which are there because we cut our expansion of this perturbative quantity to cross-section at certain order, so we become sensitive to these non-physical scales, mu f and mu r, and they are the source, one of the sources of uncertainty on our predictions. Okay, so we will show this factorization of cross-section into hard and soft parts appearing in many things. One of them is the so-called R ratio. I will show you some. We will be calculating on the blackboard, so you will see some concepts here on the slides, and then we'll move to the blackboard. So the R ratio in E plus E minus 2 hadrons, we will explicitly calculate it in perturbative QCD at the next reading order in the strong coupling constant.
Only one question. Can you again explain what's the difference between UF and UR?
So one of them is a factorization scale that appears also in the PDFs. And one of them is a renormalization scale. I will show them in some examples, so if you wait, you will see better how these things come in slowly. Okay, so what is the R ratio? The R ratio is simply this ratio of E plus E minus 2 hadrons over E plus E minus 2 muon plus muon minus. Now it's very important to keep this in mind. At lowest order in perturbation theory, we actually take this new numerator for E plus E minus 2 hadrons and we replace it with quark anti-quark pair. The reason we can do this is at the point where the interaction happens at high energies, you have quarks, and then later on, after some time, the hadronization happens. So if we are interested in describing what is happening during the interaction at high energies, we are allowed to replace hadrons with quarks. And as long as all we are interested in is just the rate for this hadronic collision to happen and not the properties of the hadrons themselves, this replacement is okay. So hadronization happens at a much longer time scale than the production of quarks. This is, for example, the time scale where both of them happen. So the production of quark anti-quark pair happens at time scale 1 over Q. Q is your hard scale. It could be, for example, the Z mass. Whereas hadronization happens at the scale 1 over lambda. Lambda is 0.2 GeV. So you see it happens at a much later stage. So we can replace hadrons with partons. And if we do that, this ratio now becomes this ratio, where the production part is the same. So it cancels in the numerator and in the denominator, and we are only left with the cross-section for gamma star to hadrons over gamma star to muon plus muon minus. We will calculate this later on the blackboard, but for now I can give you the result directly. So it's the number of NC, which is 3, times the sum over all the quarks we have in the final state of the charge of these quarks squared. That's the R ratio at 3 level. So this is the electric charge squared, and you sum over all the quarks you have in your final state, and you multiply by the number of colors. And this is a plot that shows you the R ratio as a function of the center of mass energy here. So if you keep in mind what I said about the 3-level result, you have it here. So if you look at an energy range where only the up, down, and strange quarks are present, this is what you see from data. Our 3-level result is shown in green. That's the naive quark model result. And there's a more sophisticated result. The 3-loop QCD corrections are shown in this red line that you can probably barely see. And then you have data. This is the non-resonant region. we can't say anything about a resonant region. I can't say anything about a resonant region. So we're talking about the resonant region, the non-resonant region only here. And so what you can see is that, so you calculate the tree-level result. You have 2 down quarks, so 2 times 1 over 3 squared, plus 2 over 3 squared, multiplied by the color. The sum is 2. So this is where the tree-level result is. You can see that it's, despite the fact that it's tree-level result, it's not doing a bad job in describing the data. Obviously, the n-cubed, the 3-loop result is better. It's closer to data. But for tree-level result, this is not a bad description. Now, as we cross the threshold to producing the C quarks, we move it up in our energy. We cross the threshold of producing the C quark. Now we have 2 down quarks and 2 up quarks. So this is our result for the R ratio, 10 over 3. Here you start to see more deviations between the tree-level result and the data, whereas the 3-loop result does a better job in describing it. And then as we move up in our energy, we cross the threshold of producing the B quark, and this is what we see. This is the tree-level result. Now you have 3 down quarks and 2 up quarks, and you just sum the corresponding charge squared times 3. You get 11 over 3, which puts you here. So you see that it's, it's not accurate, but it's not a very bad result, it's tree-level result. So simple leading order QCD, which is the green line, roughly describes the data. QCD at higher orders in the strong coupling constant, which is this red line I was talking about, does a very good job in describing the data. And so we will calculate only this quantity R up to the NLO level, but the results exist beyond that. And as I said, there are technical details associated with the non-resonant region. I can't tell you anything about that, so we are talking only about the non-resonant region. I cannot tell you anything about the resonant region. Okay, so that was the first part. We'll move into calculating the R ratio on the blackboard, starting with the leading order. And if you would like to take a break for 10 minutes or so, that would be okay. How do we move it up? Okay, so we will look at the R ratio, as I said, and we'll start with the leading order part, and then probably that will be, once we do it, probably will be a good stopping point. We start tomorrow with the next leading order part. So, So when we defined the R ratio before, we had both the off-shell photon and the Z. We're not going to take any contributions from the Z simply because at the energies we are studying for the R ratio, which as you have seen before, they were ranging anywhere between 0.5 GeV all the way to 10 GeV, the Z contribution is going to be suppressed. It goes like S over mz squared. So those are suppressed. So we will look at the contribution of the photon by itself, the off-shell photon. And so this is the part we are going to look at because the production part cancels between numerator and denominator. And so this is, as you know, this is finite in 4 dimensions. It can be calculated in 4 dimensions. This is finite. We're going to start with the amplitude squared. First leading order amplitude. So this is a finite quantity. If we want to calculate the amplitude squared, we can do it in 4 dimensions. But I'm going to do it in d dimensions just because we will need this piece later on. So let's write the amplitude at 3 levels. So we have Im0. That's minus u bar of P1. IEQ, just to refer to the charge of the quark. Gamma mu P of P2 multiplied by the polarization of the photon gamma star. So if we want to calculate the averages, amplitude squared summed over final state spin and color and averaged over initial state spin and color. In this case, we have only the photon polarization, and since it's an off-shell one, we have 3 polarizations. So we have 1/3, and we still have to sum over the final state spin and color of M0 squared. And I can sum over the final state color, so I have 1/3 NC times the sum over the spin of my amplitude M0 squared. What this is now. So now we are going to take the square of the amplitude times the star of this, so the complex conjugate. This means I have 1/3 and C So this is my amplitude, and I will multiply it with the complex conjugate, which is V bar of P2 gamma rho You could probably move maybe up if you cannot. Can you see, or? Does it help already, or? Okay. So we're calculating the amplitude times the amplitude squared. I'm going to remove this outer, or I can leave it for now. And so we're going to use some known formulae that you've seen before, namely the sum over spin and color This is P1 slash delta ij, sum over spin and color for the other case, B I2, B bar J2 is P2 slash delta ij. And for the photon case, sum over the polarization this is simply minus G mu nu plus P gamma mu P gamma nu over S, S here being the momentum of the photon squared, the form momentum.
So you treat as a quark as massless?
The quarks are massless, right, yeah. So you can, I'm not putting all the indices in here, but if you put all the indices explicitly in here, you will see that you will have a trace to perform, especially once you replace all these relations explicitly in there. So we have the sum. I didn't put the sum here. spin and color. Sorry?
One question, naive one probably, but where's the factor of 1/3 coming from?
That's averaging of the initial state photon, which is optional photon in this case. So you have 3 polarizations.
It's just the polarization of the photon.
Right, yeah.
Question.
Yeah.
And the photons are massless, but we're sitting at
No, it's not massless, it's an off-shell. It's not,
no,
it's,
sorry, I should have said photons, it's the quarks. If the quarks are massless, but we're still under 91, under the Z mass scale of 91 GeV or 80 GeV.
right,
Some
so,
of the quarks are heavier than that, so I don't understand.
no. I don't understand myself what you said, so.
Maybe, like if the quarks are massless, doesn't this calculation have to take place? Am I being stupid? Doesn't this calculation have to take place above the quark mass scale?
No, this is for the R ratio. So we are looking at we are far away from the Z pole at this point. So if you are talking about the Z pole, we are far away from it. We are looking at energies between, let's say, 1 and 10 GeV.
And are we only looking at the tiny quarks, the ups and downs?
So U, D, C, S, B.
All of them.
Yes, it depends on the energy scale that you are looking at. As you cross the threshold, you start to account for. So right now we are summing over all the quarks we have in the final state. But to know which ones you have in the final state, it depends on which energy range you are at. When you cross the threshold for, say, producing charm, you start to add it. When you cross the threshold for having a B, you start to add it too. Yeah. So summing is all you can do now. You sum over all the final states. All right, so the sum over the spin and color of M0 square. Once you replace all these equations, will give you NC times the quark charge squared times 1/3 times a trace of P1 slash gamma mu P2 slash gamma rho times minus G mu rho plus P gamma mu P gamma rho over S. And so now you have 2 terms to consider. One of them is the product of the G mu nu P's times this term, times this trace. And the second is the product of this term, which depends on P gamma, times this piece in here. And you will see that this one will not give a contribution. So, let's take minus G times the trace this is simply the trace of P1 slash gamma rho P2 slash gamma rho.
Sorry, can you quickly to see why that second term is
I will calculate it explicitly, we'll see, yeah. So we're looking at the first term in this product, which is this right-hand side. And so now we are going to use a relation for this. So gamma mu P slash gamma mu in general is 2 minus T times P slash. So we'll be applying that to this right-hand side. You can put the rho up here. And so if I apply it to this term, this one becomes, once I use this equation in here, becomes simply 4 times d minus 2 times p1 dot p2, because the trace of p1 slash p2 slash is 4 times p1 dot p2. I use that relation in here, and this simplifies into 2 times d minus 2 times s. Again, s here is the 2p1 dot p2. So that's one term. And then we have p gamma mu, p gamma rho divided by s times the trace of p1 gamma mu p2 slash gamma rho. You have to keep in mind that p gamma mu is actually the sum of p1 plus p2. And so if I come to this trace now, let's do it for explicitly probably. So we have p gamma mu, p gamma rho divided by s times the trace. This will be 1 over s trace of p1 slash p gamma slash p2 slash p gamma slash. And now if I come here and I replace p gamma with p1 plus p2, you can see that we will have p1 squared and p2 squared terms, and those are 0. Okay? So this term, once you replace p gamma with p1 plus p2, will give you 0. Because p1 squared is 0 and p2 squared is 0. And so at the end of the day, I can write the result here, I guess. Our amplitude squared at tree level is just 4/3 times the color factor nc times 1 minus epsilon times the charge of the quark squared times the center of mass energy S. And in principle, we can do this in 4 dimensions. All you have to do is now substitute epsilon with 0, and that's the 4-dimensional result. But we will need it later on in d dimensions, so we have it in d dimensions. So that's the amplitude squared at tree level.
But you said in d dimensions every of the particle.
Sorry?
If you do it in d dimensions, do you use it for every of the 3 particles or for the optical particle?
So you're just working in d dimensions.
So what's d dimension of every of the particles, right? So the u goes from 0 to d minus 1.
So working in d dimensions allows you to get all this. I honestly don't understand the question. What is d dimension?
He's asking if you're promoting all of the external fields to be d-dimensional.
Yeah, for now, yes. I mean, you can work in 4 dimensions. You don't have to. For tree level, you don't have any singularities to deal with or anything like that. So you can work in 4 dimensions where everything is 4-dimensional. Now I'm assuming that everything is d-dimensional, right? But that's because I will need this result later. But for the tree level, you don't have to do that. You can work in 4 dimensions.
Why is that?
So d equals 4 minus 2 epsilon. I should have defined that. You're right. So do you have it all down? I can erase, or should I wait? So I will keep this part here and we'll move to the phase space. Okay, so let's move to the leading order phase space now. So we'll be working in the rest frame of the decaying virtual photon. So I write it explicitly here. And so what that means, our P gamma star now has just the first component, lambda s, 0, 0. You can think of this as the mass of the virtual photon. And our P1 mu, which is the quark momentum, one of the quark momentum, is E1, 0, 0, E1. Okay, so we write our usual phase space integral. We have first the flux factor. And then we have the integral over P1. The on-shell delta, delta P1 squared, ddP2. Over 2 pi to the power d times 2 pi delta P2 squared times the conservation delta P gamma minus P1 minus P2. Okay, so we will solve the conservation delta for P2. For P2, which tells me that P2 is P gamma minus P1. So if you go now to the phase space integral and you remove that, what you'll be left with is 1 over 2 square root of s times 1 over 2 pi to the power d minus 2 times ddP1 delta of P1 squared delta of P gamma minus P1 squared. So we remove the integral over P2. So now going back to the result that we have seen for the matrix element square, you can see that there is no angular dependence in this result. So the fact that we have, let's write it explicitly, no dependence of m0 squared on the angular direction of P1 what this means, this is an isotopic decay. This is what we call isotopic decay of the photon. And that means whenever I have an angular dependence on my phase space, I can go ahead and do the integrate over it because I have nothing in the matrix element that depends on the angle. So I can go ahead and integrate over the angle. Yeah?
Is this a feature of the fact that it's isotropic in the restaurant? Is that a feature of the massless limit that we're taking for the quarks?
You can say that, yeah. The mass definitely makes things different if you add it. Okay, so we are going to integrate over the angles. So my phase space in this case, first of all, is written this way, ddP1 delta of P1 squared. I can write it in terms of the energy, E1. So dE1 over 2 times E1 times E1 to the power d minus 2 times d omega. And I will do this integral now because there is no dependence of the matrix element on any angle, so we can just go ahead and replace this with omega d minus 1. So this will be omega d minus 1 over 2 times the energy integral, which is dE1 times E1 to the power d minus 3. And just to remind you, omega d by itself is defined as 2 pi to the power d over 2 divided by gamma of d over 2. And this will be used. Okay, so I can remove, I guess, this one here. Okay, so we go back to our leading order phase space and plug everything in here. So we've got 1 over 2 times square root of s times 1 over 2 pi to the power d minus 2 omega d minus 1 over 2 times the energy angle times the conservation delta of S minus 2 times P gamma dot P1. And this I can write as square root of S times E1.
I'm doing this photos for the institute. It's okay for you?
Yeah, that's fine, yeah. So P gamma dot P1, you can just look it up from here, and that's what you get, square root of S times E1. And now we use this delta. Use the delta function to remove E1. And what that means, when you solve for this, E1 is simply the square root of S over 2, and there is a Jacobian, which is 1 over 2 times square root of S. Okay, so once you plug everything back again, the phase space integral becomes 1 over 2 square root of S times 1 over 2 pi to the power d minus 2 times omega d minus 1 over 2. We're just putting all the factors together here, times square root of S over 2 to the power d minus 3. And so if we are interested in just the 4-dimensional result, in d equals 4, your omega d minus 1 becomes just 4 pi. And so the leading order phase space is just 4 pi over 64 pi squared, square root of S, and this is 1 over 16 pi times square root of S. So that's our 4-dimensional leading order phase space. It's just algebra. You have questions? So now we get to the R ratio itself. R0 is going to be the ratio of our product of the amplitude squared times the leading order phase space. For the case where we have hadrons, or in our case here it's QQ bar, divided by the muon plus muon minus squared, which are going to be different from the quark-anti-quark case only by the charge. The quarks have the charge EQ squared, whereas for the muons it's just 1 when you square it. And so when you put these things together, you get what we have seen already on the slides before. NC, which is the number of quarks, it's equal to 3 times the sum over all the quarks of the charge of the quarks squared. And just to be clear here, we only sum over quarks. For which the square root of S is greater than twice the mass of the quark. So only once we cross the threshold, which means that we have active flavors. Okay, so this is the derivation of the R0, the R ratio at 3 level. This is what we have seen earlier. And this is the result that, even though it's a 3 level result, he didn't give a bad description of, not too bad description of the data. I think we will stop right now at this point here. We will pick up the NLO calculation tomorrow. And we will start to see things associated with infrared singularities, and we move on to the infrared safety concept.